Welcome everyone. It is 3 p.m. and it's time for the Server Room show. This is episode 71. I think the one of today will again be a two-part episode because I try to collect as much information as possible on today's topic, which is OpenVMS, and the ones of you who know it's very big and exhaustive topic, and there is a lot you can say about OpenVMS and the history behind it. And at some point, for sure, I will make a separate episode of DEC, the Digital Equipment Corporation, which was not just a very famous company, but the one which was behind OpenVMS, VMS, VEX, and also the Alpha architecture, one interesting CPU architecture, which is it's still in use today, and many of those Alpha architectures are running OpenVMS. They also used to run through Unix, which was a Unix variant, and yeah, one day I will make a separate episode of those, but the episode of today and most probably a part 2 of next Saturday will be regarded to and dedicated to OpenVMS as a two-part episode. This is episode 71, and we are getting closer to 100, but slowly and steadily we will get there. Regarding the history of OpenVMS, OpenVMS, often referred to as just VMS, is a multi-user, multi-processing virtual memory-based operating system designed to support time sharing, batch processing, transaction processing, and workstation applications. It was first announced by Digital Equipment Corporation as VEX/VMS, virtual address extension / virtual memory system, alongside the VEX 11/780 mini computer in 1977. OpenVMS has subsequently been ported to run on DEC Alpha systems, the Itanium-based HPE Integrity family of computers, and select x86-64 hardware and hypervisors, combining with the future OpenVMS 9.0 release. Since 2014, OpenVMS is developed and supported by a company named VMS Software Inc., short is VSI. The system offers high availability through clustering and the ability to distribute the system over multiple physical machines, allowing clustered applications and data to remain continuously accessible while operating system software and hardware maintenance and upgrades are performed, or when a whole data center is destroyed, for example, which we have seen very recently with the OVH data center in Western Europe. VMS cluster uptimes can go up to 70 years have been reported. VMS cluster uptimes of up to 70 years have been reported. So if you thought that Linux systems had very great uptime, which is true, then you might be amazed of some VMS clusters uptimes of up to 17 years and counting. Customers using OpenVMS include banks and financial services, hospitals and healthcare, telecommunication operators, network information services, and industrial manufacturers. During the 1990s and the 2000s, there were approximately 500,000 VMS systems in operation worldwide. I also remember one example I saw. I think it was on YouTube, a video. Most probably it's still up on YouTube, and if I can find it, I will link the show notes. Put the link in the show notes. It was showing a system running on OpenVMS, handling incredible amount of transactions per minute, and the system which was running on OpenVMS was responsible for on an airport when they scan the barcodes and the tags on your luggages, on those belts which are carrying the bags to the appropriate place on the airport, so it can be then loaded to the proper airplane prior to your departure. And you can imagine the amount of information or batch processing this system has to do to handle those I don't know how many bags per minute. It's quite a big number, and in this YouTube video they were talking about the robustness and the strengths of OpenVMS and why it was a great candidate for this for implementing this system. So just to have an idea where what kind of mission critical, so to say, systems rely or can rely on something like OpenVMS. I will try to find the link for that video. The origin and then the name changes. In April 1975, Digital Equipment Corporation embarked on a hardware project codenamed STAR to design a 32-bit virtual address extension to its PDP-11 computer line. A companion software project codenamed Starlet was started in June 1975 to develop a totally new operating system based on RSX-11M for the STAR family of processors. These two projects were tightly integrated from the beginning. Gordon Bell was the vice president lead on the VEX hardware and its architecture. Roger Gould was the project lead for the Starlet program, with software engineers Dave Cutler, who would later lead development of Microsoft's Windows NT, Dick Hustvedt and Peter Lipman acting as the technical project leaders, each having responsibility for a different area of the operating system. The STAR and Starlet projects culminated in the VEX 11-780 computer and the VEX-VMS operating system. The Starlet name survived in VMS as a name of several of the main system libraries, including Starlet.olb and Starlet.mlb. With the introduction of the MicroVEX range, such as the MicroVEX1, MicroVEX2 and MicroVEX 2000 in the mid to late 1980s, Digital released micro-VMS versions specifically targeted for these platforms, which had much more limited memory and disk capacity. Micro-VMS kits were released for VEX VMS 4.0 to 4.7 on TK50 tapes and RX50 floppy disks, but discontinued with VEX VMS version 5.0. Beginning in 1989, a short-lived distribution of VMS named Desktop VMS was sold with Workstation systems. It consisted of a bundle of VMS, DEC Windows, DECnet, Box cluster support, and software that was designed to help non-technical users set up their workstations without any assistance. Desktop VMS had its own versioning scheme, beginning with version 1.0, which corresponded to the version 5.x releases of VEX-VMS. In July 1992, Digital renamed VEX VMS to OpenVMS as an indication for its support of open systems industry standards such as POSIX and Unix compatibility, and to drop the VAX connection since the port to Alpha was underway. The OpenVMS name was first used with the OpenVMS AXP version 1.0 release in November 1992. Digital began using OpenVMS VAX instead of VAX-VMS with the version 6.0 release in June 1993. The port to DEC Alpha in 1988, after the cancellation of the Prism project, Ken Olsen asked Bob Supnik to investigate ways that Digital could keep the performance of VAX VMS systems competitive with RISC-based Unix systems. A group of engineers known as the Extended VAX or EVAX task force was formed, who originally attempted to produce a RISC-like subset of the VAX architecture. When this approach turned out to be a dead end, the group began investigating the feasibility of porting VMS and its applications to a clean slate RISC architecture. The group decided to adopt the Prism architecture with modifications, which eventually became the Alpha. The project to port VMS to the Alpha architecture began in 1989 and booted successfully on a prototype Alpha EV3 based Alpha demonstration unit in early 1991. Prior to the availability of Alpha hardware, OpenVMS was developed and booted on an emulator named Mannequin, which implemented many of the Alpha instructions in a custom microcode on a VAX 8800 system. The main challenge in porting VMS to a new architecture was that VMS and the VAX were designed together, meaning that VMS was dependent on certain details of the VAX architecture. Furthermore, a significant amount of the VMS kernel layered products and customer developed applications were implemented in VAX macro assembly code. To port the VAX macro code to for this purpose, the macro32 compiler was created, which translated VAX macro to Alpha object code. Digital also created a VAX to Alpha translation facility known as the VAX Environment Software Translation, short for VEST, to convert VAX executables where it was not possible to recompile the code for Alpha. The VAX compilers for high-level languages, many of which had their own bespoke code generators, were converted to use a common compiler backend named GEM. Certain low-level details of the VAX architecture, such as interrupt handling and atomic queue instructions, were embedded in PAL code, which further minimized the amount of changes required to port the VMS kernel to Alpha. The VMS port to Alpha resulted in the creation of two separate source code libraries based on a source code management tool known as the VMS Development Environment, or VDE, for VAX and for Alpha. The Alpha code library was based on a snapshot of the VAX-VMS code base circa around version 5.4-2. 1992 saw the release of the first version of OpenVMS for Alpha AXP systems, designated OpenVMS AXP version 1.0. In 1994, with the release of OpenVMS version 6.1, feature and version number parity between the VAX and Alpha variants was achieved. This was the so-called functional equivalence release. The decision to use the 1.x version numbering stream for the pre-production quality releases of OpenVMS AXP caused confusion for some customers and was not repeated in the subsequent ports of OpenVMS to new platforms. When VMS was ported to Alpha, it was initially left as a 32-bit only operating system. This was done to ensure backwards compatibility with software written for the 32-bit VAX. 64-bit addressing was first added for Alpha in the version 7.0 release in order to allow 64-bit code to interoperate with older 32-bit code. OpenVMS does not create distinction between 32-bit and 64-bit executables, but instead allows for both 32-bit and 64-bit pointers to be used within the same code. This is known as mixed pointer support. The 64-bit OpenVMS Alpha releases support maximum virtual address space size of 8 TB as of a 43-bit address space. I don't know if it's terabyte or TB bytes. It's T lowercase I B, maybe it's a TB bytes. You can definitely have a look at the show notes because I might be mistaken there. Most probably I am mistaken there because it's a T lowercase I B, not TB as in terabytes. So it looks a bit like that gigabytes I saw. So I think it should be TB bytes. So what a strange name. Which is the maximum supported by the Alpha 21064 and Alpha 21164. One of the more noteworthy Alpha-only features of OpenVMS was OpenVMS Galaxy, which allowed the partitioning of a single SMP server to run multiple instances of OpenVMS. Galaxy supported the dynamic resource allocation to running partitions and the ability to share memory between partitions. I will have to look more at this feature somewhere in the future because it sounds a lot to me like when we discussed some of the features of IBM's AIX Unix and the type of virtualization AIX is capable of. Some of these features resonate very familiar with those, so I would love to see if there is a direct relation from one to another, and I will probably put in the show notes if I figure that one out. The port to Intel Itanium in 2001, just prior to its acquisition by Hewlett-Packard, Compaq announced the port of OpenVMS to the Intel Itanium architecture. The Itanium port was the result of Compaq's decision to discontinue future development of the Alpha architecture in favor of adopting the then new Itanium architecture. The porting began in late 2001 and the first boot took place on the 31st of January 2003. The first boot consisted of booting a minimal system configuration on an HP i2000 workstation, logging in as the system user and running the directory command. The Itanium port was accomplished using source code maintained in common within the OpenVMS Alpha source code library with the addition of conditional code and additional modules where changes specific to Itanium were required, whereas the VAX and Alpha architectures were specifically designed to support the low-level needs of OpenVMS. Itanium was not. This required certain architectural dependencies of OpenVMS to be replaced or emulated in software. Some of the changes included the extensible firmware interface, EFI, is used to both OpenVMS on the Integrity platform, taking over the role of the system reference manual SRM firmware on Alpha. Support for ACPI was also added to OpenVMS, since this is used to discover and manage hardware devices on the Integrity platform. For Itanium, the functionality which was implemented using PAL code for Alpha was moved into a component of the OpenVMS kernel named the Software Interrupt Services, SWIS. The Itanium port adopted a new calling standard based on Intel's Itanium calling convention, with extensions to support the OpenVMS common language environment. Furthermore, it replaced the OpenVMS specific executable formats used on the VEX and Alpha with the standard executable linking format, ELF, and dwarf formats. IE754 was adopted as the default floating point format, replacing the VEX floating point format that was the default on both the VEX and Alpha architectures. For backwards compatibility, it is possible to compile code on Itanium to use the VEX floating point format, but it relies on software emulation. The operating system's internal structures were extended to support the 50-bit physical addressing available on Itanium, allowing 1 PB, I think, again, because it's P lowercase I B of memory to be addressed. The Itanium port otherwise retained the mixed 32-bit, 64-bit pointer architecture, which was introduced in OpenVMS Alpha version 7.0. As with the VEX to Alpha port, a binary translator for Alpha to Itanium was made available, allowing user mode OpenVMS Alpha software to be ported to Itanium in situations where it was not possible to recompile the source code. This translator is known as the Alpha Environment Software Translator, AEST, and it also supported translating VEX executables, which had already translated with the VEST tool. The Itanium port was officially named HP OpenVMS Industry Standard 64 for Integrity servers, although the name OpenVMS i64 is more commonly used. 2 pre-production releases, OpenVMS i64 version 8.0 and version 8.1, were available on June the 30th, 2003, and on December the 18th of 2003. These releases were intended for HP organizations and third-party vendors involved with porting software packages to OpenVMS i64. The first production release, version 8.2, was released in February 2005. Version 8.2 was also released for Alpha. Subsequent version 8.x releases of OpenVMS have maintained feature parity between the Alpha and the Itanium architectures. The port to x86 to 64, when VMS Software Inc. VSI announced that they had secured the rights to develop the OpenVMS operating system from HP, they also announced their intention to port OpenVMS to the x86-64 architecture. The porting effort ran concurrently with the establishment of the company, as well as the development of VSI's own Itanium and Alpha releases of OpenVMS 8.x. The x86-64 port is targeted for specific servers from HPE and Dell, as well as certain virtual machine hypervisors. Initial support was targeted for KVM and VirtualBox. Support for VMware was announced in 2020, and Hyper-V has been described as a future target as well. The x86-64 port is built from the same source code library as the Alpha and the Itanium architectures, using conditional compilation to manage the architecture-specific code needed to support the x86-64 platform. As with the Alpha and Itanium ports, the x86-64 port made some changes To simplify porting and supporting OpenVMS on the new platform, VSI adopted the open source LLVM compiler backend, replacing the proprietary gem backend used in the Alpha and Titanium pods. A translator was developed to map the gem IR to LLVM IR, allowing the existing compiler frontends to be reused. In addition, the open source CLang compiler was adopted as the officially supported C++ compiler for OpenVMS under x86-64. On x86-64, OpenVMS makes more extensive use of UEFI and ACPI to detect and initialize hardware on boot. As part of this, VMS is now booted from a memory disk instead of the traditional VMS boot mechanism, which relied on boot drivers containing a basic implementation of the file system and which was tied to specific hardware devices. The changes to the boot process necessitated the creation of a dump kernel. This is a secondary kernel which is loaded in the background at boot time and is invoked in case OpenVMS needs to write a crash dump to disk. OpenVMS assumes the presence of 4 hardware provided privilege levels to provide isolation between user applications and various parts of the operating system, while x86-64 nominally provides 4 privilege levels. They are only equivalent to 2 of the privilege levels on the VEX, Alpha and Titanium. In the x86-64 port, the Software Interrupt Services SWIS module of the kernel is extended to emulate the missing privilege levels. As with the Titanium port, the calling standard for x86-64 is an extension of the platform standard calling convention, specifically the System 5 AMD64 ABI. Certain characteristics of the x86-64 architecture created challenges for defining a suitable calling standard. For example, due to the small number of general purpose registers for x86-64, the macro32 compiler has to store the contents of the emulated VEX registers in an in-memory pseudo registers structure instead of using the processor's hardware registers as is done on Alpha and Titanium. The first boot was announced on 14th of May of 2019. This involved booting OpenVMS on VirtualBox and successfully running the directory command. Later in 2019, the first real boot was announced. This consisted of the operating system booting in a completely standard manner, a user logging into the system and running the directory command. In May of 2020, the version 9.0 early adopters kit release was made available to a small number of customers. This consists of the OpenVMS operating system running in VirtualBox VM with certain limitations. Most significantly, little to no layered products are available, and code can only be compiled for x86-64 using cross-compilers which run on Titanium-based OpenVMS systems. Following the version 9.0 release, VSI has released a series of monthly updates which add additional functionalities. These are designated version 9.0-A, version 9.0-B, and so on. This is how far we got in this episode, and in the next one I will talk more about the OpenVMS architecture, a bit about the kernel, its command language interpreter, those privilege modes, some of the features, and some other interesting bits and pieces. I think that will be enough for part 2, and most probably we're not gonna need a part 3. Thank you very much for listening, and see you next Saturday in episode 72, part 2 of OpenVMS.